Hi guys, this is the lesson for 1-2. The goal of this lesson is to learn the vocabulary words so you can describe the behavior of a graph with, better words than like up and down and dotted line and, connected line. A better word than curvy. Okay, so if in class or on class kick, there is a 24 graph activity, but we're going to go right into the notes for the video. Okay. A relation is a mapping between input and output value. The domain is the x values or inputs in a given relation. Now, they could be x values in a coordinate pair. The domain could be x values in an input-output table. The domain could be the x-axis. Anything we associate with x values would be the domain. Domain is related to your independent variable. The range are the numbers that are your y values or your outputs in a given relation. That connects back to your dependent variable, anything to do with y. So we have examples of different kinds of relations, okay? A relation can be a graph. A relation can be this thing right here. It's not very common, but let me try to explain to you how this middle thing works. Okay, so let's start with a value of -3. Okay, the left-hand side is always the domain or the x values. So a -3, if we were doing a coordinate pair, would be the x value in a coordinate pair. The arrow or the line, sometimes they're lines, sometimes they're arrows, connects up with the 2. -1 connects up to -5. Okay. Why would anybody do a mapping like this where you have all the x values on one side and all the y values on the other side and they don't all connect up? Sometimes that's because they're x values or y values that repeat, and rather than list them multiple times, they only list them once. In this case, it looks like they put all the x values in order from least to greatest, all the y values in order from least to greatest, and then they just connected the ones that are supposed to go together. This is not a common thing for you to see, so I want to show it to you, but don't worry too much about it. And an input-output table, too much. An input-output table is also a relation. So what makes a relation a function? Okay, so a relation is a function depending on officially. The official thing is for each value in the domain, there is exactly one value in the range. That means for any particular x value, it only has one unique y value. Well, that's really still a pretty abstract idea, so let me show you what that means. In a graph, you have to pass something called the vertical line test. And it's exactly what it sounds like. I'll take a vertical line, and if I take that vertical line and I drag it across the graph, the blue line and the red line are making an X in only one place. As I keep dragging it, they only cross in one place. But bam, I get on this side of the graph, and the blue line and the red line cross at two places. They cross here, and they cross here. So that means that this graph right here fails the vertical line test. The graph underneath it if I take a vertical line and run it across my screen, across this graph, it only ever touches one part of the red line at a time. It never touches two like it does in the graph above. So that's the vertical line test. Okay. In one of those kind of wacky tables, okay, if every value in the domain or x value can only have one y value, then the fact that this positive 3 in the domain is pointing to two different y values. Okay, that means the same x value has two different y values. That makes this not a function. If we circle back around to this graph, I'm going to ballpark the coordinates here. This x value is about negative 0.5 or negative 1/2 for the x value, and the y value is about 1 1/3. This point down here has the exact same x value, negative 1/2, and it has a different y value. I'm going to say negative 1 1/3. This looks about the same, looks symmetrical. Okay, so they have the exact same x value, but two different y values. Okay. If we look at the input-output table over here, all I want to look at are the inputs. As long as they are all different numbers, this is a function because they are all different numbers. 1, 2, 4, 5, and 7. Okay? So this is a function. Not a function. Okay. Last thing, we have coordinate pairs. Are these coordinate pairs a function? Same thing. Look at the x values. 2, 3, 2, negative 5. The 2 and the 2 match, and they have different y values. That's a 3, that's a 9. That makes this also not a function. We have two different ways that when you make a graph, you start with the input-output table to find out where you're going to graph points, and then I would say 85% of the time we're going to connect the dots into what's called a continuous graph. So you get some points on the graph, and then you connect them to make a curve or a line or a combination of those things. And the reason that you connect the dots is because the values that are in between are possible. In other words, you can have, if you're measuring in minutes and the thing that you're measuring can, it can take 30 seconds, then it's a continuous graph. So an example would be heating up water over time, okay? Miles driven compared to gas in the tank. The graph that we see here is months versus height. Okay, when you think about how you grow, maybe from one doctor appointment to another doctor appointment, maybe you grew 3 inches. Well, you didn't like grow those 3 inches 1 inch at a time. You grew them millimeter by millimeter by millimeter, bit by bit by bit, teeny bits. So all those bits in between connect together. Okay, you are always growing until you become an adult. Miles driven compared to gas in the tank. Here again, you're losing your gas little by little by little. It doesn't disappear in big chunks separately. It's easier to think about it when we talk about discrete graphs, which is the other kind. Okay, discrete graphs are when we plot the data, but we would not connect the dots. Okay, the values that are in between the x values can't happen. All right. This graph is fees for overdue books, measuring the days they are overdue compared to their late fee. Okay, so if you've ever thought about having an overdue book and having to pay a late fee, if the book is 1 day overdue, it looks like it's, I don't know, maybe $1.75, I'm estimating looking at the graph. Okay, but it's not going to be any different if you come in the morning on that day or in the evening on that day. That entire day, that's going to be the fine. Okay, there's not going to be any time when the fine is going to cost exactly $1. It's below $1 for 1 day and looks like $1.50 for 2 days. I may have said $1.75. I meant just 75 cents. So it looks like 75 cents for 1 day late and $1.50 for 2 days late. But if it's a day and a half late, it's not somewhere in between. So we can't connect those dots because the values in between don't matter. It doesn't matter if it's a day and a half late or a day and 3/4 late. It doesn't make the jump to the next price or the next late fee until it's a full 2 days. Okay. Other examples would be like age compared to sport division. Okay. If you play a sport, you know that you age up by your birth date, and it doesn't matter if if you're league age 12, then you're league age 12 for an entire year, and you don't change. There's no league age 12 and a half. There's no league age 12 and 3/4. It doesn't change until the next whole age goes by. Miles over the speed limit compared to the amount of the fine. If you get a speeding ticket, they don't, if it's 2 miles over the speed limit or 2.5 miles over the speed limit, the speed doesn't, in between, that decimal amounts of speed don't matter, basically. It's only whole numbers that matter. So we would not connect the dots for that because only the whole numbers matter. Take a look at these graphs. Why do you think that Matthew put these graphs in the same group? All right, Ashley has these graphs in a group together, and she says, I group these graphs together because they showed vertical symmetry. If I draw a vertical line through the middle of the graph, the image is the same on both sides. Is she right or is she wrong? And they're trying to trick you here. So let's talk about what symmetry means. Symmetry means, and it talks about vertical line here, but we're not talking about the vertical line test. Okay, symmetry means that if I take a line and I put it in the middle of the graph, it looks the same on both sides. Okay, so that one looks symmetrical. My highlighting doesn't look symmetrical, but the graph does. If I move over to here, my dots are perfectly across from each other, across that vertical line. this graph is symmetrical on both sides. Where they're trying to get you is at this graph, graph V, okay? And T is also symmetrical. It's just not symmetrical around the y-axis. T is symmetrical at the bottom of the curve, which you're going to learn in future lessons called the vertex, but it is still symmetrical when I put the vertical line down through the vertex. In V, if I put the vertical line through the vertex, it doesn't look symmetrical because the left-hand side of the graph is longer than the right-hand side. But what we have to remember is graphs, although they don't show it on these pictures, remember your calculator doesn't have arrows at the ends of the graph. Okay, your calculator screen will not make arrows. So what I want you to know is that when the calculator screen runs out of room and the line keeps going, the arrows are implied. So if I extend the line past where the screen stops showing it, the two sides really are symmetrical. Dwayne said that he grouped these graphs together because each graph goes through two quadrants. Okay, just a reminder what quadrants are. Quadrants are the four sections of the coordinate plane. So this graph, the line is in this quadrant and this quadrant only. Okay, so that's two. M, yep, both of those quadrants. P, both of these quadrants. T, two quadrants. But if we go back and we remember that graphs extend, okay, so I'm going to extend the y-axis here. This is the graph where they're trying to trick you. And I extend this graph. Okay, this is going out and out and out. Then this graph also goes into quadrant 1, but it's off the screen so you don't see it. Okay, so Dwayne is wrong. Judy grouped these four graphs together but did not provide any rationale. Why are these grouped together? Take a look at these graphs and think, why would these graphs be grouped together? Let's take a look at this function here, this graph. Is this graph a function, and how do you know? What is the label for the domain? It's either the y-axis or the x-axis. One of those is the domain. Is the graph discrete or continuous?